So how is it that the volume, variety, and velocity driving big data pose such a challenge to traditional relational database technology? Did the internet break SQL? Well, the answer to that is no, as we'll see later. But the internet is pushing the hardware and architecture behind traditional relational systems to their breaking point. So why is this? Why are traditional relational database management systems struggling? Because they're delivering slow performance at cloud scale, with millions of concurrent users being theoretically managed by a single massive server. And traditional systems are also inflexible for the needs of cloud-scale data, where you're trying to cram continuously evolving data models into tables with rigidly enforced relational schema. So again, why are businesses currently stuck here? You see, software systems have evolved to largely follow a three-tier approach. You've got the client, you've got the application server, and you've got the database server. But there's a big difference in how the second and third tiers traditionally operate. Application servers evolved rapidly to a shared nothing architecture. They scale horizontally or out. Do you need more power? Throw another box on the rack. And another. On the other hand, most relational database servers work completely differently. The fundamentals of relational technology demand them to share everything. So instead of scaling out, they scale vertically or up. If you need more power, buy a bigger server. Again and again. You might even imagine some big old relational database company would want its own hardware division to keep selling you a bigger box every few years. But I digress. The point is, how a system scales matters a lot. You can keep replacing your box, but your box is going to hit limits long before your data volumes taper off. This is why cloud-ready systems scale out consistently across all three tiers of the software stack. You just keep adding commodity boxes, or managed container instances, to your stack and removing them as your data volumes ebb and flow with the seasons. Systems need this elasticity. There is another key architectural difference between the traditional relational approach and the new engaged approach to data management. See, relational systems write to disk first. Then they log records for availability, and then they eventually cache the data indexes to memory for faster access to all that data spinning around on the disks. The engaged approach is completely different. Data is immediately cached in memory. Then it's replicated within the cluster to maximize availability, and then it's written to disk. As a result of this approach, all reads and writes can be served immediately from memory, which is a critical performance edge for massive systems with demanding users. And there's another architectural limitation to traditional relational systems, and that's tables. Table-based relational database systems were invented back in 1970 and first commercialized by Oracle Corporation in 1979, back when disco was cool. And if you need to store a new type of data, you need to plan it out, build the tables, normalize them, design their relations, draft and optimize all the queries you're going to need to get the data back out in the shape that your code actually requires. Because software focuses on objects, these ever-changing things like people and places and products, not association species qualifiers, whatever those are. Of course, there's nothing new to the idea of object-oriented software. That's not the problem here. The problem is that relational database operations are expensive. Your big data box needs to seek out different tables somewhere on its disks, and then assemble that data in memory in the shape required by a particular query. Yes, complex object relational mapping frameworks have evolved in response to this to handle some of the coding labor. But the fundamental mismatch between tabular and object-shaped data leads to complex code that's expensive to maintain over time. Now, the problems with relational databases have been known for a while, and some helpful strategies have been developed. If you need performance to offset all those slow seeks on disk, well, try adding a caching layer. If you need to scale beyond one big box, you could try sharding your database across a cluster. Of course, then you're going to need some pretty elaborate code or system in place to keep track of everything for all of those join operations you're still going to need. And if you want something more flexible than rigid table-based schema, you can always store denormalized data documents in a common table. All of these approaches are useful. So useful that if you wanted performance, you should design a memory-first architecture built around the obvious benefits of optimized data caching. If you want scalability, why not build elastic clustering directly into the system with fully managed replication and failover processes? And if you want flexibility, you could focus on data document storage and then build in powerful querying, indexing, full-text search, and analytics. I wonder if someone has done all this already. So what have we learned here? Well, relational database management systems scale up to bigger hardware, not out. Scale-out architecture has been proven in the application tier. Engaged databases take it to the persistence tier. Relational architecture is disk-first for durability. Engaged databases are memory-first for performance. Relational systems have enforced schema in tables and rows to save disk space because it used to be scarce. Engaged systems leave the schema implied to make use and coding flexible over time. Relational systems try to keep up with caching and table shards and blobs and so on. Engaged systems build all this right in and optimize it for scalability and speed. We've got a lot more ahead introducing you to the new trends in database management. We hope you stick around.